hooking and DLL injection. And it's much more powerful and flexible than most people give it credit for. There's a lot of things you can do with memory manipulation if you know what to manipulate. So right now we have read process memory, the first iteration of memory reading. It's pretty simple. I mean, you make sure the memories has the read-write protection so you can read it, set the protection back. Write process memory is the same thing except you're grabbing a value instead of setting one. So forgot to mention in the beginning, a lot of my code examples have been taken from actual projects, but they're kind of minified to fit the slide. So if you see like a mistake, it's just because I was stupid when I was putting the code up on it. And then we have using memory from injected code, which if you're an injected DLL, you can just create a pointer to address dead beef in this case, which might have a structure there. And then you can access it like it's memory in your own program, which is still nice, but there's better ways we can do things. So then we have remote memory redirection. And I'd like to say I could take credit for this, but I'm pretty sure someone has done it before me. So I first came up with this when I had to read a chunk of about 40 kilobytes with read process memory from remote process, because I didn't want to be injected. And it's like, that's really slow. You can cache it, but it's not going to be fast enough. So what do? You inject your DLL into the target process as little as possible. You create a shared memory segment. You freeze every thread in that process, and then you scan the .text section of that binary in memory and find every reference to the address you want to read. You're going to replace that address with the address of your shared memory chunk, and then you're going to copy what was ever there to your shared memory. You resume all the threads in the process, you grab a handle to the shared memory segment in your loader, and you use a redirected memory at will within your remote application. So now you're sharing memory with a remote process that has no clue you're there. So to do that, you got the code. You're going to, of course, inject the DLL, create a thread, create your remote memory segment, or your shared memory segment, replace whatever constants, and then return out. And then from your loader, you're using the memory in the remote process as if it's your own memory. So really nice little trick if you're trying to work with remote memory in big chunks. It's only going to work with statically allocated memory, of course. If you want to do it with dynamic memory, you've got to hook their allocator and stuff, and it gets kind of messy, and I'm not sure what you can do with it since you don't really know what's there when it's allocating and deallocating, but it's a nice little trick. Then control flow manipulation. So I'm pretty sure most of you know, I mean, it's going to be hooking, code injection, DLL injection. Most of you have probably seen this. So it's manipulating memory in a way which impedes or changes a process's intended control flow. And like I said, you're probably going to inject your code, and then you'll just be hooking. If you're trying to stay hidden and trying to be effective, thread synchronization comes into play, and this is one thing a lot of people do wrong, and it causes programs to crash or whatever. So you want to make sure when you're working with the memory of a remote process that you're in sync with it. And we're going to go over how to do that. And this will allow you near complete ownership of a process, making the assumption that you have targeted that process specifically and you've reversed it and you know what you want to achieve. So this is more of a targeted attack. Like I said, it can be used in game hacking, or if you're trying to exploit a system and a certain program might be running that you're trying to get information from, this is something you might want to use. So the first step would be code injection. Code injection is executing injected code, which we call code caves, within a target process. And we can do it in 3 easy steps. We'll allocate the chunk of memory where we're going to put our code. We'll write a block of assembly code to the allocated chunk with one of our memory functions, in this case, write process memory. And then we're going to force the remote process to execute that code using create remote thread or thread hijacking, which is something we're going to discuss a little bit later. And usually you're just going to inject a DLL with this and then do everything from inside there. You're probably not going to create code caves for everything you want to do. So here's a simple DLL injection code cave, and I see some faces that are kind of like, no, you just create remote thread on load library A. I don't know why you made it so complicated, and we're going to get to that later. This is how you would do it using thread injection, so we'll talk about that. Or I should go back and explain it. So we just grab the address of load library, store that for later. We'll allocate a chunk of memory for our code cave, and then we just have like a little assembler class, and we're going to push the registers and flags to the stack, then push the argument of our DLL name. We're going to push load lib and then pop it into our EAX register, and that just saves us from calculating offsets. And then we're going to call EAX, and then we're going to pop the registers and flags back into place. We're going to push some instruction pointer, which we'll talk about later, and do a return, and that's just a simple way of doing a jump, because you always return to the top of the stack. So after we have that code cave written, we're going to write it to memory, and then we're going to copy our DLL name into place, and then return that to whatever might be using this. Hooking, so once we've injected a DLL using that, from our DLL we can do what is called hooking, and that is redirecting function calls from an injected library. And it comes in a few flavors. We have IAT hooking, which there's also EAT hooking, but I'm not going to discuss that because it has drawbacks. There's SEH hooking, which you will see a lot in debuggers because they use exceptions to handle code hooking. And then there's actual code hooking, which is just replacing a call to a function with a call to your own function. Of course, they're usually done from an injected DLL, and you can use hooking to change function parameters, manipulate return values, block function execution, or synchronize your malicious behavior with the target process. So we have IAT hooking, and what that does is you can hook calls to specific API functions within the scope of a specific module. You do this by changing the function address in the import address table, which is a table in the PE header, where it lists what DLLs it uses and what functions it calls. So you replace the address that is put there at runtime when the process starts with your own address, and it'll call that. It's not too effective, though, if the process knows you're going to be doing this to it, because there's obviously ways the process might store this in its own table that you don't know about, so your function will never get hit. So be careful about that. And there's SEH hooking, which is hooking portions of code by triggering a vectored exception handler. And you're going to do that by maybe putting an interrupt 3 breakpoint on that piece of memory, interrupt 2D, or maybe you set the memory to no access. Whatever you want to do to trigger an exception handler to handle when that piece of code is hit. And then there's code hooking, and this is the simplest of the three. It's just changing the location following the call operation to your own location, so the process of calling your own function. So IAT hooking, we're just going to grab the PE import table of the target module. We're going to locate the desired API function in the list. We're going to store that original function call in case we want to call it, and then we're going to replace the original address with our proxy address. So the first step is to grab the import table. So we look at the beginning of the module, we find there's a DOS header, we look for the optional headers, which will be the actual PE header, and then we're going to see if it has an import table. If it has an import table, we return that import table, and then we can go through the thunks in that import table, which we'll see in 2 slides. And for each thunk, which is each DLL, we will loop through all the functions that are imported from that DLL, and if we find the one we're looking for, we're going to go ahead and return the address that stores the call address of the function. And then that's all tied together right here. Of course, we'll grab our import table, and then if it's not there, we're just going to be like, yeah, we can't do this. If it's there, we're going to loop through it every thunk, and we're going to go until we find the function. This isn't actually doing a DLL name check, so if you have functions that are like in 2 different DLLs, you have to do that. But we're going to loop through every function that is being imported, and once we find the one we're looking for, we're going to go ahead and hook it. And we're just going to do that. Of course, we're going to do virtual protect on the memory because it only has read access at this point. We're going to set our original to the one that's already there. Then we're going to point to our new function address. Then we're going to set the protection back in case anything's watching. Then there's SEH hooking, which is a little more complex. The first step would be to create a vectored exception handler, and then you want to place whatever exception. In this example, we're going to use setting the memory page to no access. But this is really slow because you're going to end up single stepping through every instruction in that page. This is a special case, and we're going to explain why later. And then once you have your exception in place, which in most cases you probably just want to use an int3 breakpoint, You can catch those exceptions, execute whatever callbacks or whatever code you want, and then you're going to restore the code to normal. You're going to take out your exception. Then you're going to set the trap flag, which is going to tell the operating system, execute this one operation, and then jump back to the exception handler. And that allows you to put your exception back in place. So whatever was there before gets executed properly, and then you can put your exception back in place for the next time around. So you're going to set the trap flag, you're going to return continue execution, you're going to catch a single step exception when it comes back, you're going to put it back in place, and then you're going to do continue execution. The program's going to go on like nothing happened. So first step, we create our vectored exception handler if it's not there, and then we're just going to add the hook that we want to a list of hooks to be executed by our handler. And then in the handler itself, if you look at the first if clause, you'll see that it's checking if it's a single step and if we have replace hook set, which is just the variable that tells us what the last hook we called was. And if those two are met, then we're just going to set the memory back to page no access, which is the exception that we're using in this case. And then we're going to set replace hook to 0, of course. Now, if you look at the else if, we're checking if it's an access violation. If the exception's an access violation, we're going to loop through every hook that we have set up, and we're going to see, okay, is this one of our hooks? And if you want to check if it's on the same page in this case, because of course we're using a no access hook, so when you set memory protection, it affects a whole page, not just whatever bytes you set it to. So check if it's on the same page. Now, if it's on the same page, but it's not the actual function call we want to hook, we're going to just return continue search, and because, wait, yeah, I think I might have minified that wrong. But yeah, we're basically going to return without calling our callback because we don't care about that. We only care if the hook, the active hook, is the operation we want to execute. And if it is, we're going to set our flags to OX100, which is our trap flag. And then we're going to execute our callback, and then we're going to put the memory protection back to normal, which is going to allow it to execute normally until our single step. Once again, you probably want to do this with an int3 breakpoint, so you're not playing with the whole memory page, but I'll explain why we did this later. And then there's code hooking. So you're going to locate the address of the call that you want to hook. Then you're going to calculate the offset to your proxy function, which is going to be the address of the proxy function minus the address where your hook is at minus 5. You can read your current offset if you plan on calling that function, store it for later, and calculate what that function actually was. And then you're going to replace the current offset with the offset of your proxy function. That code's pretty simple. Calculate our address, do your virtual protect, of course, then just copy the memory into place. You don't even have to really play with the actual call opcode. I've seen where someone will like make an array with the call opcode first and the 4 bytes for their function, but you don't need to do that because it's already in place. You just go ahead and put your offset, and then it'll call your function instead of what's already there. And then when you're doing hooking and you're working with memory within the process, you want to make sure you're in sync. I ran into a problem where a program that I provide for users is Lua scriptable. And they want to be able to define things in the Lua scripts that are operating on the same thread of this remote process that doesn't know that they're there. So sure, you can do that. You want the Lua scripts to be able to sleep, so they're running in their own thread, but you want to make sure you're not calling a function or reading memory or doing something while the actual program's trying to do it too, or you're going to crash, and users aren't going to be happy, or someone's going to realize there's some malware there. Whatever you're doing is going to get found out because you're breaking stuff. So this is critical to stability. So the first way is with a peak message hook. Most programs are probably going to call peak message in their main loop over and over, waiting in their message handler. So if you go ahead and hook that, then you're going to unlock some mutex, you're going to sleep until a variable is 0, and you're going to lock it again. And then you're going to return the original peak message because we don't care about what happens with it. But then within your worker thread, you can increment that variable telling the peak message hook that, hey, I need a work. Then you can lock your mutex, do whatever you need to do, unlock it, and then you decrement that variable again, and it will return execution to the program. So it's basic thread syncing, a basic threading model, but you have to do a little trickery to get there because, of course, the process doesn't know you're there. And then there's thread hijacking. This is a little more inefficient, and it's more for targeted things like if you're trying to call a function externally and you're not going to be doing it a lot, you might want to do this. Or if you're injecting a DLL that's going to lay down a bunch of hooks, you could freeze a process from within the DLL itself, or you could use thread hijacking, which goes back to that the code cave we saw earlier and why it was a little bit more complex than most injection routines. So you're just going to get the main thread ID of the process which you're trying to inject the code into. You're going to suspend that thread, and then you're going to store the current execution pointer of that thread somewhere. You're going to set the execution pointer to the address of your code cave, which is you've already allocated, you've already created your code cave. Then you're going to set the execution pointer of that thread to the address of your code cave. You're going to set the end of the code cave to jump back to the original EIP that you stored, and then you're going to resume the thread. And this is basically making the process's main thread jump into your function and then jump back to where it was without having to lay down any actual code. And you're just, the code is just open the process. You're going to grab the thread ID. You could do like get window remote thread process ID or main thread process ID, whatever. Or you can look at the thread information block, which is a structure that every process has. And it's going to be at the same address within every process on that system. So you can just look at the FS register plus OX18, which is where it's going to be stored, or the thread ID is going to be stored for the main thread. You can grab the thread that way, or my bad, you can grab the thread information block that way, and then at offset OX24 from that is the main thread ID. So then you can read that from memory, you have the main thread ID, you can open that thread, suspend it, grab the context, put your execution pointer in place, put your code cave in place, and return. And then it's going to execute your code cave, jump back into the process, and it's like nothing ever happened. And then there's handle manipulation, and I'm pretty sure everyone in here has used Process Explorer. Does anyone know you own Process Explorer, and then you have the pane at the bottom? You can see all the handles that are held by the processes. Well, I wanted to know, how do they do that? Because you can close mutexes, you can close handles down there, and I was like, how do you do that? And I needed to close a mutex on a remote process for a project I was working on, so I was like, okay, I want to do this in code. So I did a little bit of research. There was a site called ntinternals.com, I believe, really good site for NT system internal documentation. And I had to use a lot of functions that were found on there. But basically, what handle manipulation is manipulating handles held by remote processes. We have mutex state manipulation as an example, and modifying or writing to a file that may be held by a remote process. You maybe can't open that file because it has full access to it, so you can grab the handle from the remote process and write to that file. Like I said, we're going to use a handful of undocumented NT functions, and this will enable us access to otherwise inaccessible objects. So the first step, we're just going to loop through all of the system handles using NT query system information. We're going to grab all the handles owned by the target process, add them to a vector. We're then going to duplicate whatever handles we want to work with into, well, we'll duplicate all the handles initially into our target process using NT duplicate object. Once we do that, we can use NT query object, and using NT query object will give us the ability to read the names of those handles and other information about them, so we can see what handle, we can find whatever handles we might want to manipulate. And then we can work with them as normal once they're duplicated into our process. If we want to close the handles in both our process and the remote process, you can use duplicate close source flag to the NT duplicate object function, and then when you call NT close on the handle in your process, it'll close the one in the remote process as well, which is really handy for mutexes. So, like I said, the first step, we're just going to do a query system information. If we don't have enough data in our buffer, we're just going to do it again because that's how NT functions like to work. We're just going to do a query system information for the handles, then we're going to loop through what's returned, and then we're going to push that back to a list of our handles if the owning process ID is the one we care about. Once we have that list of handles, we're going to loop through it. That'll be in the next slide, but we can look at each handle individually, and we can do an NT query object on the name info to get the name of that handle, and then check if it's the one we want to work with. And then let's say our goal is to close a mutex. We'll just duplicate it with close source, and we'll call release mutex on it like normal, and then we'll call NT close. Now we've released the mutex globally, and we've closed it in both our process and the remote process. Now if our target's a file handle, or you can do this with name pipes as well, I believe, so if you want to manipulate a pipe or whatever without grabbing it or creating a new handle to it, you can go ahead and grab the handle from the remote process. You can call write file on it, and then do whatever else you want, write file, read it. So to tie that all together, we'll go ahead and enumerate process handles. We'll loop through them all. We might have a name of a mutex we're targeting and a name of a file we're targeting, so when we find those, we'll just call our functions on them as an example. I found that really useful in the sense of if there's a program that only lets you execute it once, and then it's like, hey, instance is already running, a lot of the time they're going to do that with a mutex if they're not just calling find window on themselves. So you can just go ahead and close that mutex and open as many instances as you want. And then there's staying hidden, which kind of ties it all together, because whether you're making a piece of malware or you're doing game hacking or whatever else you may be doing, you probably don't want to be found for a number of reasons, and this probably isn't a substitute for a good, if you're doing malware at least, this isn't a substitute for actual stealth, but it gets the job done for a lot of purposes. So of course it's going to be eluding the gaze of prying eyes. We have some tricks with the process environment block and hiding any injected libraries you might have from debuggers and reading the module list and whatever else, because the process environment block stores all of that information. We have a few functions you might want to look at if you're looking at implementing a Userland rootkit. And then we have some debugger detection stuff. And along with the debugger detection stuff, we just have a few tricks to keep debuggers away if we detect them. This will put to use some of the techniques we've discussed, and it's going to be critical for most applications of these techniques because you're probably doing this with some malicious intent. So first you have the PEB module list manipulation, and the PEB is stored at FS plus 30. It's actually a child of the thread information block. And so we can read the PEB loader data, which is at the address of the PEB plus 12, and then it's going to have a list of all the modules in that process. It's going to have them stored in a linked list, so we're just going to unlink it. Now you have 3 linked lists that stores the different modules. You're going to have the initialization order, the memory order, and the load order. You can loop through one of them because it's actually one node with 3 different front and back pointers. So once you find it in one list, you can just unlink it from all of them and get out of there. So go ahead, grab the process environment block. And then like I said, we just loop through it. We see if the base address of the module in the linked list that we're looping through is the module that we want to hide. And if it is, we're just going to go ahead, we're going to, just for safe measure, we're going to erase the name that's there. We're going to zero out that memory. And then we'll unlink it and we'll break out of there. So now if you load up the process in a debugger and you go to a module list, you won't see the module there. If the process tries to scan all the modules that are in it, it won't be seen there as well. So that's a nice little trick if you're not using manual mapping and you're actually still injecting your DLL with load library. And then there's the rootkit implementation. I'm not going to have any code examples for this because you can't really fit that in slides, but I'll kind of explain some of my reasoning behind it. You'd probably use an SEH hook for this, or you could use detours, which is you got to kind of write a disassembler that can check lengths of opcodes, so you can place a jump in the beginning of a function you want to hook, and then in your code cave, place the operations that were there and then jump back. but I would just use the SEH hooking using int3 breakpoints. So you drop an int3 in the beginning of these functions that are listed over here on the left to hook them, then you do whatever. Maybe you drop it at the end because you want to modify return values, whatever. But the intent is, with query system information, for example, under all functions that can give you a list of processes or any of system information or a list of handles running, it's going to call NT query system information. So if you hook that in every running process, you can spoof what every running process is going to see. The only thing that's going to not be affected by this is a driver, of course. So hook that in every running process. You can spoof what processes are running. Task manager won't see your executable, whatever it may be. And then there's NT query virtual memory, and anything that's going to be scanning big blocks of memory, read process memory and write process memory also, I believe, we'll be calling this. So if you don't want something to see what's in a certain part of memory, you can spoof the return values on this function as well. NT query directory file is the underlying function that the kernel will, well, no, not the kernel, but the NT subsystem will use to see what files are in a given directory passed to it. So if you hook that, maybe you want to look for a prefix on a file name or a certain extension, and you can hide that from the list that's returned for the files in that directory, and then whatever's looking won't see those files. It will work on Explorer. It'll work for any process that is trying to look at stuff. So, and then there's query attributes file, which is just going to, you can modify the attributes that are returned from a file. So maybe you appended some bytes onto the end of a file, but you want it to look the same size. You can spoof the return value here. So like maybe you modified some file or whatever, and then it's going to checksum itself when it starts, some kind of integrity check. You can just say, hey, it's this size. My bytes at the end aren't there. And it'll be like, okay, whatever. And then there's NT create process. And if you are doing a rootkit implementation, you probably want to inject into every process as it's created before its main thread starts. So if you hook create process, you can make sure the process is created as suspended, inject into it, and then resume that process and pass it back to whatever originally called the function. And then the manual DLL mapping is the reason I showed an SEH hook using memory access, because maybe you want to manually map your DLL into the remote process. So you allocate a chunk the size of the DLL, put it in there, put your import table and your export tables together yourself, do whatever else you need to do. But you put a page before it at page no access. And if the program's scanning its own memory, trying to see what's there, you're already out of the module list, but maybe it's scanning memory looking for signatures. Put a page no access before your library and use that SEH hook on it. And if something tries to scan that page, you're going to get a callback to your exception handler, and then maybe you want to get out of there, maybe you want to stop it from doing what it's doing, whatever you want to do. It's not going to be able, well, you can stop it from being able to seeing your library below that page. And then there's debugger detection. Maybe like me, you do game hacking, and the user knows it's there, so you don't really need a rootkit to hide. Maybe you need it to hide from the game. But you don't want the game company or any competitors reverse engineering your software. So you want to detect any debuggers that might be there. So maybe you're going to check remote debugger present. You're going to call that API function, but that's not enough. Maybe you're going to hit a 2D and an int3 interrupt and see if they're handled by an exception handler. Okay, that's a little bit better because most debuggers are going to handle those. Well, there's also a flag in the process environment block you might want to check. And that's just going to tell you, Boolean, am I being debugged or not? And then you can check if there's a RIP exception handler, which is an exception that's only thrown by debuggers. And then you can check if output debug stream sets, or string sets an error code. Because if it returns 0 when you call getLastError after calling that, then there is a debugger there allowing you to call that function. And if you do find that there's a debugger, there are many ways to tell that debugger that like you can't see what's here. I mean, of course there's ways around that too, and there's ways around those, and there's more ways to detect debuggers, but those are outside this scope. But you might want to corrupt the memory. Maybe you want to, this one's specific to OLEDBG. There's an exploit in OLEDBG where if you pass format strings into output debug string, it passes those into printf, but it has no argument. So OLE itself is going to crash, because it just called printf with format strings with no extra parameters. Or you can use set process is critical, which if you set a process to critical and it has debug rights and the process dies, the whole system's going to blue screen. So it's going to kill their VM. It's going to, I've done this to myself in development. I forgot that I've had this in a process in release mode, and I've tried to debug in release, and I've blue screened myself probably 50 times. So, I mean, it even fools me, and I'm the one who implemented it, so it's useful. I mean, people get around it, of course, but. So first you have is remote debugger present. It's just a win API function, and of course, if a debugger knows you're looking for it, this obviously isn't going to return true, so you'll check for their breakpoint handlers. They might get around this. So you check if there's any hardware breakpoints set on the thread context. Or not, yeah, for that thread, you want to check if there's any hardware breakpoints. If there's not any hardware breakpoints, like I said, check if the PEB shows the debugger. And then check output debug string. And there's other ways. Maybe you want to scrape the process list and check if your parent process in the process tree is a debugger process or whatever else. I mean, I'm sure we all know millions of ways to detect debuggers, so. RIP exception handler. And then there's hindering analysis, like I said. You just grab the set process is critical from NTDLL, and then you call it on your self process. Now, if there's a debugger that is attached, but it's not setting actual SE debug privileges, you'll have to set those yourself. Because if you set a process to critical that doesn't have debug privileges, it's going to be like, so what, I don't care, and it's not going to blue screen. So you might have to set those yourself. But once you set it, call set is critical, then you can call exit on your process. And as soon as exit is called, the whole system will blue screen because the critical process died. I also have the output debug string in there, and like I said, that's an OLE exploit. There used to be one for IDA, where you made two jumps jump to each other, and now this doesn't work anymore, they fixed it. But if you made two jumps jump to each other, when they pulled it up in IDA in graph mode, even if the binary wasn't running, it would go into an infinite loop trying to graph those jumps going back and forth. That doesn't work anymore. But, I mean, we're all hackers in here, so if you're really trying to evade debuggers, you go in, you find some exploits, you put them in your code, and you can crash those debuggers as soon as they're found. You can even make your code handle those bugs in a way that you just execute the code that would bug out the debugger, but not your own process. You don't even have to detect it because it's crashed itself out. And that's it. You can go ahead and scan the QR code, and there's some code samples. The link's also at the bottom. I just threw that together last night. It's not actually like geared towards this presentation, but it's more of projects that took me towards doing this that I've learned from. And so I've just put those all in a RAR for anyone who wants to look at them. So that's it. Thanks.